Good morning, dear students. So in the last class we have started just this motion of center of mass. Just brief idea I have given about the motion of center of mass. So once again we will revisit the basic concept first, and after that few example based on that. Motion of center of mass. Okay, so as we know, if a system of particles are given, their center of mass is defined as RCM is equal to M1R1 plus M2R2 and so on by M1 plus M2 like this. Here M1, M2 are the particles and R1, R2 are the position of those particles. That also can be said as a center of mass location of those particles from a certain reference point. So the system has center of mass RCM is this. Now if we are looking at change in the center of mass of the system, it means if these particles are changing their position. So R1 is going from R1 position to let R1 dash, R2 from R2 to R2 dash. It means different particle of the system is changing their position. Then the center of mass of the system also changes position. So for changing center of mass we can write, and that change may be because of the motion of these particles or may have some forces or some acceleration. Because of that, the position of the center of mass is changing. So we can write here change in position of center of mass can be written as delta RCM is equal to M1 delta R1 plus M2 delta R2 likewise by M1 plus M2 like this. This we can write. To see here, delta RCM, change in center of mass. Okay, so change in center of mass will be happen only when the particles are either in motion or some force is acting. If external force, if external on a system is absent and all the particle of and initially the center of mass of system is at rest. This is a very important point here. If external force on a system is absent and center of mass of system is at rest, or we can say if F external is equal to 0 and VCM, velocity of center of mass, is also 0, then delta RCM, the change in center of mass of system must be 0. So this is the conditions here. If these conditions are there, external force on the system is 0 and center of mass velocity, center of mass is not moving, then delta RCM is equal to 0. Then we can write, so M1 R1 plus M2R2 likewise will be 0. It means even the different particles are moving, but their motion will be like that. The M1 into change in position of M1 plus M2 into change in position of M2 as well as plus M3 into change in position of R3 or M3. This will be always 0. But this will be true only when external force in the system is 0 and center of mass of the particle is at rest. A few examples we will discuss on the basis of this first of all. See. Let, for example, two-point masses having mass M1 and M2 kept at distance L. Example, let's see. Let two particles of mass M1 and M2 kept at distance L, assuming no force between the particle except on the particles except mutual gravitational force. Mutual gravitational force. Now, when the system is released, when the system of particle release, find the distance traveled by individual particle just before colliding. Find the distance traveled by particles just before colliding. This is the question. Okay? The question is this: the two particles are given, these particles having mass M1 and M2 kept at distance L. And this is the important point, assuming no force on the particles except mutual gravitational force. It means between the particles only one force is there. That force is your gravitational force. Gravitational force is always attractive force and it is equal and opposite. See, on this particle gravitational force in this direction, on this particle gravitational force in this direction. Now, if you are considering this as a system, let this be your system. So since in the system, if we are looking here, these are the equal and opposite force. The net force in the system is your 0. Net external force is 0. And the system is released. Release means initial velocity of the center of mass was 0. External 0. And initially your VCM is also your 0. It means external force is not acting in the system. Velocity of center of mass is also 0. Then delta RCM, the change in position of center of mass will be 0. It means center of mass will not change its position. Now, where is the center of mass? It is just like a two-particle system. Let center of mass is here. And from here, add distance r1. From here, add distance r2. So, one equation you will have r1 plus r2 equal to L. Another equation, as we know, for two-particle system, product of mass into distance here equal. So, m1 r1 equal to your m2 r2. Okay. So, what will happen here? Now simplify. Substitute the value of r1 from here to here, or r2 from here to here. So you will get r1 is equal to your r1 value if you are writing here. R2 your m1 r1 by m2. So m2 by m1 plus m2 into n. And r1 r2 will be your m1 by m1 plus m2 into n. See, then what will happen here? As soon as you will release, these two will move toward the center of mass, but center of mass will not change its position. So these two will collide like this. These two will collide like this. It means that block M1 has traveled distance R1 and M2 has traveled distance here R2 just before colliding, because center of mass is not moving. So they are moving in such a manner that they are keeping the center of mass of system at the same place. Okay? So note down this and see another example. See another example. This is plan. This is a man of mass m. The question is this: a man of mass m is standing at one end of plan kept on a smooth horizontal surface. Kept on a smooth horizontal surface. Okay? Kept on a smooth horizontal surface. Now man start walking towards other end of plan, other end of plank. Find the displacement of plank when the man is on the other end. Find the displacement of plank when man is on other end. Okay, this is the question. A man of mass small m is standing at one end of plank having mass capital M, length that you can say L. One end of plank of mass M, capital M, length L. Okay, here you can write one end of plank of mass capital M and length L, kept on a smooth horizontal surface. Now man start walking towards other end of plank. Find the displacement of plank when man is on other end. Okay, see how to solve this. First of all, man and plank both initially at rest. So center of mass velocity is 0. Next, when we are making FBD of the system, because we have to check the external forces. When we are making FBD of the system, so we will have gravitational force downward, normal force here upward. So the forces are only in the vertical direction. This is your system. This is your system. So here your downside of gravitational force. From here your normal force. This system. So no force in the horizontal direction. No force on a system in horizontal direction. No force on a system in horizontal direction. So as we have found in the last, you can say, point, if VCM is 0 and no force on a system in a particular direction, so displacement of the center of mass will be 0. So delta RCM in which direction? In a horizontal direction will be 0. It means center of mass of a system in a horizontal direction will not change. This is the main point. Now, how to calculate this one? The center of mass of system in horizontal direction will not change means M1 delta R1 plus M2 delta R2 and so on. It should be equal to 0. See here. Now, how to calculate this one? See, initially here, this is your plan, this is your man. Okay, this is your man. So center of mass of plank is let us C1 and center of mass of man is here C2. This is your initial condition. Okay, east. And now when the man start walking, so plank will also move. Why? It will move. First of all, man will walk only when there is a friction between the plank and man. So friction force on the man in the forward direction, while friction force on the plank in the left side. Because of that, plank will move. So see here. When man is reaching here, the plank will go in that side. Let plank is here and man is here. So this is the displacement of your plank, x. Let x. So x displacement of the plank means center of mass of plank shifted here now. C1 dash, new position. This is your x. And man is moving from here to here. Man center of mass C2 here. Now it is C2 somewhere here. So this distance will be your total length of the plank was your L. So this is now your from here to here L minus x. Okay. Now you can substitute. M1 let your plank. Plank mass your capital M. Plank mass your capital M. We have to find x value because the question they are asking find the displacement of plank. We have to find the value of x. So M1 mass of the plank, delta R1 displacement of plank. Left side, there are two displacement here, left and right. We can define the direction. Left side we are considering as negative and right displacement we are considering as a positive. The plank displacement your left side is negative. How much displacement of the plank of center of mass? X. So it will be a minus x because left side. Plus M2. M2 is the next body. Next body is a man. Mass of man your M. Delta x R2 displacement of the man from here to here. How much? L minus x. In which side? Right side. It is positive. And this is equal to your 0 because delta RCM is not changing. Horizontal component is 0. Then we will have ML is equal to your M plus M into x. X is equal to your ML by M plus M. The answer. The displacement of plank is your ML by M plus M. Understood? Note down this. Now see another example. See another example. See, a particle of mass small m, a particle of mass small m released from the top of a triangular wedge of mass capital M. Okay, particle of mass small m released from the top of a triangular wedge of mass capital M from a height h as shown in diagram. As shown in diagram. Assuming all surfaces are smooth, assuming all surfaces are smooth, find the displacement of wedge, find the horizontal displacement of wedge when particle is reaching at the bottom of the wedge. When particle is reaching at the bottom of wedge. The bottom of wedge. Okay, see, the particle of mass small m, this is a particle of mass small m released from the top of a triangular wedge of mass capital. This triangular wedge, top is here, height h, from a height h, as shown in diagram. Assuming all surfaces are smooth, all surfaces means surface between wedge and ground, surface between wedge and mass, block or particle, all are smooth. So what you have to find, as soon as it releases, it will start coming down. So wedge also start moving horizontally. Why the wedge will move? If you will see the FBD, in your FBD, if you will see, only vertical forces are there. Vertical forces are gravitational down and upward here normal, just like here. No horizontal forces there. Yes, between mass, between wedge and block, but normal force is there. But normal force on the wedge as well as on the block. So these normal forces are equal and opposite, so it will cancel. But if you will see the individual FBD of the wedge and mass. So normal force on the wedge on this side, normal force on the block will be in this side. So one normal component, this normal component of on wedge have horizontal component. Because of this horizontal component, wedge start moving in the left side. But overall, if you will see both together, so this is equal and opposite, it will cancel. So there is no horizontal force in the system, only forces are in the vertical. And initially system was at rest, the same condition. Initial horizontal velocity of the system was 0. No force on a system in horizontal direction. So if initial velocity 0, forces are also 0. So delta RCM in which direction? Horizontal will be 0 because horizontal forces are not there. The center of mass of component of horizontal component will remain here constant. So here also delta RCM is equal to 0. It means this is which direction? In horizontal. Okay, so horizontal component of center of mass of system will not change. Same process we will do here also. Same process. See. So our relation will be M1 R delta R1. Same way we can write M1 delta R1, but we have to write in horizontal direction equal to C. See. So first this is the initiator. Block is here. M, capital M, theta is here H. Okay? This is your initiator. This is your initiator. Center of mass, since this is your particle here, dimension your 0. The center of mass of wedge we can assume somewhere here. Let this your C1. Center of mass of this is let your C2. Okay. These are just we can assume anywhere. Now, as the block start moving, wedge will go in that side. So then the diagram will be like this. Now this is reaching here. Now C2 will be here, and this displacement at your x we have to calculate. C1 earlier it was here, now it is somewhere here. Sorry, C1. Okay, earlier it was here, now it is here. How much displacement? X. In which side? Left side. Mass of this here M. Same process. M1 capital M. Same rule. Left side I will take negative. Right side your positive. C1 your left side. How much? X. M into plus M2 mass of this your particle. And displacement of this horizontal means this. So this is the horizontal displacement. So this is your equal to total length, this minus x. So this is your h, let this length your l minus x. Go to 0. Now here, so you will have x is equal to again ml by, and what is L? L is not given. In terms of h you can find. So here you can do your cot theta. Cot theta is equal to your L by h. So how much L? H cot theta, substitute here. X is equal to your m by m plus m h cot theta. This is the displacement of wedge when the ball is reaching. Okay, so note down this. Now come to the next point. Velocity and acceleration of center of mass. As we know, as change in position of center of mass is given as m1 delta r1 plus m2 delta r2 and so on by m1 plus m2. Likewise we can write. Okay. Now, so velocity of center of mass. Velocity of center of mass, VCM, is rate of change of position of center of mass equal to time rate of change of position of center of mass, or this we can say delta RCM by delta T. So VCM is nothing delta RCM by delta T. It means in this we can divide by delta T, so we will get the result. So M1 delta R1 by delta T plus M2 delta R2 by delta T. Likewise we can write by mass M1 plus M2 like this. VCM can be written as M1 V1 plus M2 V2 by total mass, like this, where V1, V2 and V3 are where V1, V2 are the velocity of center of mass of a particle of system, velocity of center of mass of different particle in a system, of different particles in a system. Okay. Similarly, we can write acceleration also. Similarly, we can write acceleration of center of mass of system ACM is equal to same time rate of change of position of equal to time rate of change in velocity of center of mass of system, or we can say delta VCM by delta T. Okay, so ACM can be written as delta VCM by delta T. Same thing here, delta VCM by delta T. We can write here M1 delta V1 by delta T plus M2 delta V2 by delta T, likewise by mass. So ACM can be written as M1A1 plus M2A2 and so on by M1 plus M2, likewise. Now where A1, A2 are acceleration of different part in the system, acceleration of center of mass of different particular bodies in a system or bodies in a system. Okay, now this is another relationship. See one important point here. As M1 plus M2 equal to capital M. Capital M is the total mass of system. Total mass of system. So this we can write here. So then M into ACM can be written as M1A1, M2A2 like this. So, okay, let's note down this. Okay, now see, from Newton's second law, MACM, F external equal to MACM. We can say here F external force equal to here M1A1 plus M2A2 likewise. Now this further I can write F external M1 A1. A1 is nothing, delta V1 by delta T. Delta V1 by delta T plus M2 delta V2 by delta T. Now condition, if F external equal to 0, if it is 0, then see here, then see this equation. If 0, so what will you get? M1 delta V1 plus M2 delta V2 and so on. Okay? So as we know, see, as linear momentum momentum P is equal to mass into velocity. So change in linear momentum delta P is equal to m into delta V. So this is called as a linear momentum of particle 1 or for one body, second body. So this then upper equation, this equation can be written as 0 is your delta P1 plus delta P2. Delta P1 means P1 final minus P1 initial plus this P2 final minus P2 initial. Similarly other, this further I can write here P1 initial plus P2 initial plus like this is equal to your P1 final plus P2 final like this. This is called your conservation of linear momentum. Conservation of linear momentum means when this condition will applicable, when this is equal to F external 0. It means if external force in the system is 0, okay, note, if external force in a system is 0, external force in a system is 0 in particular direction. Is 0 in particular direction? In particular direction, then in that direction, linear momentum of system will be constant. Linear momentum of system will be conserved. Okay, linear momentum of system will be conserved. So if external force in a system is 0, in a particular direction, it's important. If external force 0 in the let x direction, then momentum along x direction will be conserved. If external force 0 in y direction, then momentum along y direction is 0. If or net force is 0 in any direction, then you can conserve momentum in any of the direction. This is the meaning of this statement. So note down this. Okay, note down, and tomorrow we will discuss some example based on this theory. So just revise this all points and go through this example. And tomorrow I will explain some more example based on the velocity of center of mass, acceleration of center of mass, and application of conservation of linear momentum. Okay, thank you. Thanks a lot for all. You are bringing lunch also here?
No, sir.
Just 48. That's type class, huh? Switch off कर देना।